Yes, yes, you last.
Wait a second.
Okay. Welcome, everyone. It's my pleasure to introduce the first speaker of the semester, Enrique Carasa. He's a first-year master's student, and he will talk about this paper called Revisiting RowHammer. It's an important paper in RowHammer research because of its very in-depth analysis, rigorous analysis, and new findings, surprising findings at its own time as well. So I hope you enjoy the striking observations here. Yeah, please go ahead.
Hello everyone, I'm Enrique Carasa, and the paper I present today is Revisiting RowHammer, experimental analysis of modern devices and mitigation techniques, and it was presented at ISCA 2020. Here are the authors of the paper, if you're interested. So starting with the executive summary, the motivation behind the paper is that DRAM chips are becoming more vulnerable as DRAM chips are becoming denser, but there is a lack in academia of studies that show how this is varying. And the problem that it tries to solve is to do just that, and to also evaluate how the current mitigations and the mitigations that have been currently presented will fare in these future chips. So the goal is to do the analysis that hasn't been done, and to evaluate the mitigations on the future chips, because the paper uses the data after doing the analysis of the current chips, it uses data to predict how vulnerable will be the future DRAM chips. So the paper is the first. This paper is the first rigorous RowHammer characterization study that tests a broad range of DRAM chips. It tests different types, technology node generations, and manufacturers. And the paper finds that RowHammer vulnerability is worsening as we go to newer chips, and that the current mitigations have a reasonable performance hit on current DRAM chips, but they scale quite poorly. And as we go to newer chips, this performance hit will get worse. So the conclusion of the paper is that new mitigations need to be designed. That are capable of dealing with the future chips. So this is the outline. I'll start with to describe what is RowHammer and give a little DRAM background. So DRAM is divided into banks, and each bank has multiple rows. And when you want to access data in a row, you have to open or activate it. And when you're done with the data, you close it, which means it requires a recharge. So, but when you do this opening and closing multiple times, you will end up getting bit flips in the adjacent rows. And if you do this process even more times, you'll get more bit flips in the adjacent rows, as well as bit flips in rows that are not adjacent. But why does RowHammer happen? And to understand it, we have to look again at how DRAM is organized. So inside the banks, you have the rows, as I said, and then each row are just a vector of stored cells. And stored cells are just capacitors and an access transistor. And this access transistor is not perfect. And there is some charge that leaks from the capacitor. And that's why DRAM implements the DRAM refresh. So as you can see, over time, the charge of the capacitor gets reduced. And after a while, the DRAM refreshes the capacitor to avoid it going below the minimum voltage. Because if it goes under that value, the data gets corrupted. So as you can see, over time, there is no data corruption. However, this curve is different under a RowHammer attack. As you can see, when the adjacent rows get activated, there is an extra leakage of charge, which means that when the refresh time comes, the data might already be corrupted. And as you can see in this case, the data of the capacitor gets lost. However, not all cells are equally vulnerable due to some process variation. So as you can see, the green cell, even under a RowHammer attack, is capable of maintaining its data. So, but why is this an important problem? Well, if you look at this program, this is capable of doing the process that I described earlier. So it starts by activating row X, then activates row Y, which needs to be in the same bank as row X. And then both of these addresses are flushed, so that the next access goes straight to memory instead of going to the cache. And by doing this multiple times, we'll be opening and activating the row as I described earlier. And if row X and row Y have only one row in between, this is called a double-sided hammering, which is more effective than the previous case because you get more bit flips in the victim row. And this program, similar to the one that I described earlier, have been used multiple times to cause attacks. An example is RowHammer.js that was able to get bit flips on the browser using JavaScript. Then there is also Jammer that used RowHammer to take over the control of an Android system. There is ground pruning that uses GPUs. RowHammer that gets bit flips over a network. There's flipped phone shoe paper that uses RowHammer to break encryption keys. There's also Rambly that uses RowHammer to read bits from memory. And there's many other papers if you're interested in this topic. So now on to the motivation and goal. The motivation behind the paper, as I said, is that there is a lack of data that analyzes how the relationship between scalability of DRAM chips as they become denser is varying with its vulnerability. And the paper aims to do that study and use data to predict how how vulnerable will be future DRAM chips. And this data is then used to evaluate the proposed mitigations, as well as predict how they will fare in future more vulnerable chips. The experimental analysis was done using three infrastructure. One for DDR3 chips, which was an FPGA-based soft MC using a Xilinx ML605. Then for DDR4 chips, it was used an FPGA, also a soft MC, but this time using a Xilinx Vertex UltraScale 95. And for LP DDR4, an in-house testing hardware was used. And this infrastructure is necessary because the authors have to have control over the type of commands and their timing. They have to have control over the timing and the type of commands that are sent to the DRAM. And it's also necessary to control the temperature of the chip. So a total of 1,500 DRAM chips were used from 200 DRAM modules coming from the three major DRAM manufacturers. And the classification of nodes of the DRAM chips was using a type node notation. So the type can be DDR3, DDR4, or LP DDR4. But the classification of the node is a little bit more complex. So for DDR4 chips, the node can be 1x or 1y, depending on the technology node size. But for DDR3 and DDR4 chips, this information is not disclosed by the manufacturers, which meant that the authors had to distinguish the chips in a different way. So they use an old new node notation, and what separates old from new chips can be either the date of manufacturing of the chip or the publication of its datasheet. Yeah, and the characterization was done using worst-case conditions. So, which meant that the authors had to disable all sources of interference, such as refresh and calibration events, because they would affect the amount of hammering that you'd be able to do in one cycle. And they also disabled the mitigations, because what's interesting in this study is not to test the vulnerability of chips that are sold, but the authors were interested in the circuit level bit flips. Each test had a duration of 32 milliseconds to avoid retention time bit flips. And the access pattern used was a double-sided RowHammer that I described previously, because it's more effective than the one-sided. And the chips were kept at 50 degrees Celsius. This is the This is a general description of how the characterization was done, and I will describe it briefly. So it starts by defining the victim and the aggressor rows. Then it refreshes the DRAM. Then it disables the DRAM refresh and refreshes the victim row to initialize the counter of the 32 milliseconds of the test. Then it starts the hammering, where one hammer is equal to activating both aggressor rows. And then DRAM refresh is re-enabled, the data is sent to the computer, and the bit flips are restored to the original values to restart this process all over again. Now, there were 5 characterization studies that were done in the paper. The first one is the RowHammer vulnerability, and I will explain what each one of these means later. So the first one was RowHammer vulnerability. Then it was the data pattern dependence, the hammer count effect, and the hammer count is the amount of hammers that you did in the cycle that I described previously. Then it was studied the spatial distribution of the bit flips and the first RowHammer bit flip per chip. So the first point, the RowHammer vulnerability, the authors were interested in testing if it was simply possible to get a bit flip for a certain chip. And the answer was yes for 84% of the chips, but the vulnerability was dependent on the type and on the node. So when you go to older chips, such as DDR3, old, only 12% of them are vulnerable. Then for DDR3 new chips, 65% of them are vulnerable. And as you go to the more recent chips, such as DDR4 and LPDDR4, all of them are vulnerable. And this allowed the authors to make one simple conclusion, is that newer DRAM chips are more vulnerable to RowHammer than older ones. In the data pattern dependence, the authors tested if there were certain data patterns that were more effective than others when trying to get bit flips. And so the paper tested several data patterns, including solid and checker data patterns, and this was all done accordingly to what was described in previous papers. And these are the results. As you can see on the x-axis, you have the data patterns tested, and on the y-axis, you have the percentage of RowHammer bit flips that were seen. And the conclusion from this is that the data pattern that is more vulnerable to a certain chip is not dependent on the chip itself, but on its type node configuration. Now, moving on to the hammer count effects. These are the plots that were presented in the paper. On the x-axis, you have the logarithmic scale of the hammer count, and on the y-axis, you have the log scale of the bit flip rate of the chips. And the first conclusion that the authors make is that these two relationships are linear. And the second conclusion is that when we go from older chips to newer chips, the curve is shifted leftwards and upwards. Leftwards meaning that you get bit flips for lower hammer counts, and upwards meaning that for the same hammer count, you get more bit flips. In the spatial effects, the authors tested were answering 2 different questions. The first one was where the bit flips were occurring in relation to the victim row. So this is an example of the plot that is shown in the paper. And as you can see on the x-axis, you have the distance to the victim row. So the 0 index is the victim row, +1 +1 and -1 are the aggressor rows, and all the other rows is just other rows. Their distance to the victim. And here are the results presented in the paper for all the chips. And the conclusion is that newer DRAM chips have bit flips in more rows. And as you go further away from the victim row, you get less bit flips. The second question in the spatial distribution analysis was how many bit flips you could have in a 64-bit word. And the paper argued that there were 2 types of distributions. The first one for DDR3 and DDR4 chips, and the second one for LPDDR4 chips. So as you look for the first distribution, most of the 64-bit words have around 1 bit flip, but when you go to LPDDR4 chips, most of the words have either 2 or 3 bit flips. And an interesting observation is that there were chips that had up to 4 bit flips, which would require strongly and costly ECC, which probably means that ECC is not the best solution to mitigate RowHammer. The last point is the first RowHammer bit flips per chip. where the authors were interested in finding out what was the hammer count for the weakest cell for a certain chip. And here are the results. And a simple conclusion can be made when you go from older chips to newer chips. The HC first value gets decreased. And I forgot to say what was the HC first. HC first is the lowest hammer count where you get the first bit flip for a certain chip. The only exception for this observation that I said is the DDR4 chip from manufacturer B, where, as you can see, when you go from older chips to newer chips, the HC first value increases. And the authors argued that this was due to bad labeling of the chips. And an interesting fact is that the lowest HC first value seen was for LPDDR4 1Y, and for that chip you could get bit flips with only 4,800 hammers. Now onto the evaluation of the mitigations mechanisms. The paper analyzed five state-of-the-art mitigations and one ideal mitigation. The 5 state-of-the-art mitigations were increased refresh rate, PADA, ProHit, MR-lock twice, and the ideal mitigation is the ideal refresh mitigation mechanism, where it only refreshes the row right before there is a bit flip. The evaluation was done using a cycle-level simulator named Hamulator, and the metrics used to evaluate the mitigations were DRAM bandwidth, overhead, and normalized in performance. Here are the results presented on the paper, and I will briefly explain how each mitigation scales as we go to more vulnerable chips by decreasing the HC first value. So starting with the increased refresh rate, as you can see, the solution scales quite poorly, and it's impossible to implement this mechanism for HC first values lower than 32K. Then when you go to PADA, this is a solution that scales better, but they're still significantly overhead as you go to lower HC first values. For instance, when you go to values lower than 1K, there is at least a 28% performance loss. And when you go to HC first values as low as 128, there's an 80% performance loss. Then ProHit and MR-lock, I don't know if you can see it, but it's these 2 points over here. And the reason it's only 1 point is because the papers implemented their solutions for HC first value of 2K, and they don't explain how they would have to change the mitigation as you go to lower HC first values. So yeah, it's impossible to implement either of these mechanisms for more vulnerable chips. Then Twice has a similar problem where it's only implementable up to HC first value of 32K. Lastly, the ideal refresh rate scales much better than all the other options, and you can go to HC first values as low as 128, and you would only have a performance loss of 6%. So now it's plotted vertically, the HC first value for the lowest HC first value for each chip that was tested. And to understand this plot, you have to think that if a certain point it's on the right of a vertical line, it means that that chip is RowHammer free. And if a certain point is on the left, it means that that chip is still vulnerable to RowHammer. So as you can see, increasing the refresh rate is only a solution for DDR trivial chips, which means that this is not a scalable solution. Then the only mitigations that are capable of mitigating RowHammer for the most vulnerable of the chips tested are PADA, ProHit, and MR-lock. And PADA has an 8% performance loss when it tries to mitigate, when it has to mitigate RowHammer on LPDDR4 And the last observation is that there is still a lot of room for improvement, especially when you go to lower HC first values and when compared to the ideal mitigation mechanism. So the paper also presents some research directions going forward to design mitigations that are more scalable. And the first research direction is DRAM system preparation. So the paper argues that solutions that are DRAM based or simply implemented in the memory controller are not enough, and that some preparation between these two components is necessary. Then the second research directions are profile guide mechanisms, which are mechanisms that know or can effectively predict where a certain where bit flips are going to occur. And the paper argues that if this information was known, then the paper gives two examples of mitigations that could be implemented if this information was known. The first one is increasing the refresh rate of the more vulnerable rows, which would make increasing the refresh rate more scalable. And the second solution would be to disable the rows or to remap them to more reliable memory. So to conclude the presentation about the paper, this paper was the first rigorous analysis of a broad range of DRAM chips. Since it concluded DDR3, DDR4, and LPDDR4 chips, and it concluded that that chips are becoming more vulnerable to RowHammer. Then, about the analysis of the mitigations, they have relative low performance for current chips, but this will not. But in the future systems, the performance hit will be greater. And so the paper concludes that new mitigations need to be designed that can deal with more vulnerable DRAM chips. So I will now move on to the discussion part, where I will start by describing what I think are the strengths of the paper, its weakness, and then we'll have a discussion about the paper. So starting with strengths, I think the first one is its novelty and relevance, because it's the first rigorous RowHammer characterization of the vulnerability of DDR3 chips, as well as DDR4 and LPDDR4. And to understand why this is relevant, we have to go back when the paper was written. So recently, DRAM manufacturers had claimed that RowHammer was solved. However, this claim was later proven false by papers such as Retrospective. And so, yeah, the paper RowHammer is solved, now it's not. And the paper does a good job at taking a step back and reanalyzing the problem. It disables the mitigations of the chips and states what is the current state of the vulnerability and sets the guidelines for the future mitigations that need to be implemented. The second thing that I like about the paper was that it performs a true evaluation of the chips. Since it tested different chips, a variety of tests were performed. The analysis was done rigorously, and it tested worst case conditions. And I think it's important to do worst case evaluation and not, for instance, average case, because in a system is as secure as its weakest links. So we have to test how weak or how strong is this weakest link. The third aspect that I like is that it sets a standard for future systems by presenting what the ideal refresh mechanism would look like. And this ideal refresh mechanism is also important because it proves that DRAM scalability is possible. We just need to design mitigations that work and that are scalable. The fourth strength, in my opinion, is that it presents a new metric, which is scalability, which might seem something obvious, but in previous works, this was something that was not even considered, and it's just as important as the other metrics. And fifth, the paper presents some new research directions, which I think enriches the quality of the paper. Now, onto the weaknesses. And my first one is that the paper doesn't explain why the DRAM chips were kept at 50 degrees Celsius. So initially, I thought that this would be because this is the working temperature of the chips. But if that was the case, there would be no reason to keep the temperature at 50 degrees Celsius, because the chips would reach a temperature by themselves. So then I thought that maybe it would be because the authors were tested worst case conditions. So they increased the temperature to have more bit flips, but this would also don't make sense, because in a real RowHammer attack, the attacker wouldn't have physical access to the chip, because the attack would probably be done on the cloud. But then I talked to the mentors, and they told me that the reason why the DRAM chips were kept at 50 degrees Celsius is that in the summer, the room temperature can go over 30 degrees. So if they tested the chips at lower temperatures, it would be possible that the room temperature would increase the temperature of the chip, and they couldn't keep the temperature of the chip constant. However, this is something that the paper doesn't mention, and I think it would be important. Second one there is the labeling of the DRAM chips. As I said, for DDR4 and for DDR2 chips and DDR4 chips, the node could be either old or new, depending on certain dates. But the paper doesn't explain why certain years were used. So the choice seemed quite arbitrary. And well, I think something that proves that doesn't prove, but it shows that could be quite arbitrary, was that one of the results was explained with bad labeling. And I think this is a bad argument, because if this is an argument that could be made to disregard the result that is not expected, it could also be used to disregard other results in the paper. Last, then on the third point is how the paper analyzes scalability. Because I remember the plot that I showed you. I think it was a little bit weird, because only 2 of the mitigations that were tested were actually lines. For twice MR lock and pro hit were just short lines or points. So yeah, it just felt weird, the plot. And I think that scalability is more than what the paper presents. The paper only mentions DRAM bandwidth and performance loss, but I think scalability is more than that, and other parameters such as power consumption, extra area, and cost needed to implement the solution are also relevant when evaluating scalability. The fourth thing, my fourth critique about the paper is its writing. I'm not sure if you looked at the paper, but there are some, throughout the paper there are some observations which I think are good when you're reading the paper quickly or just trying to get a general idea of the paper. But when you're reading every sentence quite carefully, you will realize that some of the observations are just the rephrasing of what's already written in the text, and that make the paper harder to read and more less interesting. But I still think the observations are great. I just didn't like there was sometimes just rephrasing of what's already in the text. The second, and then I think there were some inconsistencies regarding how the data patterns were tested. So as you can see, this is what's written in the paper. When they are describing the data patterns used, they mention SO here, then CO, and then CH, and then RS. But when you look at the plots that are in the paper, you will see that there is RS and CH, as mentioned above, but then there is this new data pattern, which is CS, which is not described nowhere in the paper, and SO and CO don't appear. Then my last point might seem a little bit unfair, but the paper only presents empirical results and no explanation, not a physical explanation. And I say this is unfair because the authors probably don't have access to the information that would be necessary, because DRAM manufacturers don't disclose how their chips are produced. But I feel like by reading this paper, you will not learn as much about RowHammer as if there was some explanation. So now I will go to discussion, and I think instead of discussing of what's present in the paper, I think it would be more relevant to have a discussion about the takeaways that can be taken from the paper and use these results to mitigate RowHammer. So I would like to ask you some questions, and hopefully you will participate. So my first question to you is if we think that we should stop DRAM scalability or even go back, so forget about DDR4 chips or even DDR5, and just go back to DDR3 chips when they were safer.
In general, no, but maybe for some high security applications where performance is important, we can just leave it like focus on the chips.
Yeah, I think that's a valuable solution. I think I have the same opinion as you. So yeah, for critical security system, maybe it may make sense to go to DDR3 old chips and just increase the refresh rate until the chip is safe. But long term, it's not a viable solution, because technology needs to improve, and the only way to do that is by trying to find new mitigations to RowHammer. a more interesting question for me is if we should look at other types of memories other than DRAM. And yeah, do you have any emerging new emerging memory technology? And if you have any idea, please consider its security vulnerabilities. Okay. So yeah, I looked about this topic. I saw some interesting possibilities. The first one is PCM, or phase change memory. I'm not sure if you heard of it. So these are the two papers that I read about it, and they say that PCM is slower than DRAM and consumes more than twice the amount of energy, and it has a limited number of writes. But these papers made a few changes to PCM, increased the number of the row buffers to take more advantage of the locality of the programs, and this resulted in a reduced delay of just 1.6% when PCM is replaced with DRAM, and the energy consumption was around the same. And they also implemented partial writes, where instead of writing the entire row, you just write a limited number of bytes. And when you just write 4 bytes each time, the PCM lifetime can be improved to 5.6 years. Another option I saw was STT-RAM, which is spin transfer torque magnetic RAM. This is the paper that I read about it. And similar to PCM, it has around the same problems. It's slower, consumes more energy, and it has a limited lifetime. Again, this paper made some changes to STT-RAM by implementing partial writes as well, and this reduced energy consumption to just over 8% when compared to DRAM. And they also implemented the row buffer write bypass, where when you have a write memory, instead of replacing what's in the row buffer, you just write it to the memory, and you keep the row buffer, and this improves the performance by taking more advantage of the locality of the programs, of the applications that are run. It is improved performance by 6% when compared to DRAM. However, there's this recent paper that analyzes RowHammer on STT-RAM. So there are two types of STT-RAM, because STT-RAM is a non-volatile memory, and there is also a version of this STT-RAM, which is slow retention non-volatile memory. And the problem with STT-RAM is that its writes require a lot of current, and this produces a voltage bounce when writing, and this can open the word wheel. This increase in voltage opens the word line for a few seconds, and so if you write multiple times, there will be retention, will be data corruption in certain rows. However, this paper only did analysis and didn't perform the test on physical chips, not analysis, simulations. Lastly, there is non-flash memory, which is not really comparable to DRAM, because as you can see, it's much slower even when compared to PCM. But there's this paper that analyzes how RowHammer the effects of RowHammer in all types of memory, not just on DRAM, and it presented some interesting facts about non-flash memory. First is that non-flash memory is also scaling, just as DRAM, and becoming denser, and this is resulting in them becoming less reliable. There has been some cell-to-cell interference, and as well as low data retention time. And the two-step programming that non-flash memories implement can also be used to cause data corruption. So one of the solutions that the paper presented was profile-based mechanisms, and I thought that this would be an interesting idea. And so there is this paper that's called A Deeper Look into RowHammer Sensitivities, and can be considered a follow-up to the paper that I'm presenting today. And I'll focus, they tested a lot of things, but I'm interested in how the rows, the distribution of rows, of the rows vulnerability, because I think profiling would just be possible if certain rows were more vulnerable than others. And so if they were uniformly distributed across the DRAM, there would be much you could do. So in this paper, as you can see in these plots, the paper concludes that more than 90% of the rows have an HC first value, which is greater than, which is twice as great as the lowest HC first value of the chip. What this means is that if you have a chip that has an HC first value of 1K, it means that more than 90% of the rows have an HC first value which is higher than 2K. And I think this would be interesting when designing mitigations, because you would be able to have a personalized HC first value for certain or more vulnerable rows, instead of having a global HC first value for the entire chip. And this could be relevant when, for instance, for PADA, instead of having one probability for the entire chip, you could have two probabilities or even more. And more vulnerable rows would have a certain probability, and less vulnerable rows would have another probability of refresh. Another approach would be for the DRAM manufacturers to increase the redundancy of the chips that they produce. So currently, DRAM manufacturers produce more rows than the ones that are actually used, because they know that after the chip is produced, there will be some rows that will have cells that don't work. So they disable the rows and use the ones that were extra. And my idea would be that they could just increase the redundancy, and instead of just testing for working and not working rows, we would also test for vulnerable and not vulnerable rows. However, this would be a timely, expensive process, and maybe would be too expensive to implement. So now the question that I have to you is that what would be the more efficient way of storing vulnerable rows? If we wanted to implement a mitigation that uses profiling, what would be an efficient way of storing this information? Because storing the information of all the rows and if they are vulnerable or not wouldn't be very efficient. So I wonder if you have a more intelligent way of doing it.
Could use something like Windows.
Okay, yeah, that was my idea as well. So we would test the DRAM chip, and if a certain row was vulnerable, when we put the address through the boom filter, it would output ones, and when it's not vulnerable, it would be at least 1, 0. So the paper that I presented analyzed some mitigations, and it concluded that they were not scalable. However, there were some mitigations that were proposed after this paper was written, and I took a look at some of those mitigations, and I will present them to you, and hopefully we'll say if you think that this solution is scalable or not, and I will present the results of the paper, and then we can make a conclusion if it's scalable or not. So the first one is RowHammer that was written in 2021. Here is the paper if you're interested. And the basic idea of RowHammer is to count the number of access that each row had using a unified Bloom filter. And when this value is greater than a certain threshold, the row is blacklisted. And when you have an access, a row that was blacklisted and it was recently accessed, the access is considered not RowHammer free and is blocked. RowHammer also implements the attack throttler that counts the number of access that each thread had to a blacklisted row. And after the discount which passes a certain threshold, this application is considered an attacker, and it has its DRAM bandwidth reduced, leaving more DRAM bandwidth for benign applications. So do you think that this solution? Okay. So do you think that this is a scalable solution? Do you think that as the first value decreases, there will be too many rows that will be blacklisted and every program would be considered an attacker? Do you think that there will be this would require too much area? Yes.
I don't think that's a scalable solution due to many reasons, but one of those reasons is that you will need to maintain like to track too many rows in a memory, and memories have a lot of rows. I think it's technically impossible to count the number of accesses for all rows.
Okay, well, okay. The paper doesn't has like a huge table, and each entry is an address. But the paper uses a unified Bloom filter, so you have two Bloom filters, one for each. Each Bloom filter is cleaned after the refresh interval. What happens is that you put if every time you access a row, instead of the output of Bloom filter, instead of being just 0 and 1, it's increased by 1 every time you access a row. And when you want to predict the number of access that each row had, you put the address through the Bloom filter, and then you pick the minimum value of all the outputs that it had. Do you think that this is scalable, or you still have the same opinion?
So you actually don't exactly count the number of accesses for each row. That's just a prediction.
Yes, because in the Bloom filter you can have conflicts. So it can be possible that two rows add the same entry. So you will always end up overestimating the number of accesses that a certain row has.
Well, I think from that point of view, it might be scalable.
Does anyone have another opinion? Okay. Yes?
I think as soon as the HC first value gets closer to the accesses to the number of accesses let's say a normal program is doing, it doesn't work anymore, or you could throttle like the geometric programs.
But then if a program would require to access the memory as often as the HC first value, there will be no DRAM that is capable of even the ideal refresh mechanism wouldn't work, right? And the paper showed that the ideal refresh mechanism works for most applications. Okay, I think this is enough. Okay, so these are the results of the paper, and as you can see, when you go to older papers, they start including scalability in their analysis. And as you can see, there is you have here the analysis of how the performance of block hammer varies as you go to lower HC first values. And as you can see, even when you go to HC first values as low as 1K, there is minimal performance hit. So the second paper was written in 2022, and it's called Reducing Worldline Voltage. This is the paper. And the idea is pretty simple, just reduce the worldline voltage. And the paper concludes that this could in fact reduce the number of bit flips that you could have in a certain chip. However, this came at the cost of the reliability. Because the row activation time increased, the capacitors would saturate at lower voltages, and it might be required to increase the refresh interval, as well as adding 2-bit error correcting codes. So do you think that this is a scalable solution? Yeah. Do you think there is this performance on impact is something that is worth taking? Do you think this is a long-term solution? Yes?
I don't know, you are introducing another issue about the energy consumption in this case. So I don't see why it would be good for scalability.
So what do you mean by energy consumption?
Because you just said that then you have to refresh the memory.
Oh, okay, yes, that's one of the problems with this solution. Yeah, I think another problem is that there is a limit on how much worldline voltage you can reduce, right? You cannot keep reducing worldline voltage, and if you do, the RAM would just become slower and slower, and I don't think that's something that we would like. So the third paper is graphene, was written in 2020, and this is the paper, and uses this Grice algorithm that counts that tries to predict the number of access that each row had, and when this value reaches a certain threshold. Yeah, the accounts that row are blocked. So do you think that's a scalable solution when AC first value decreases? These are 3 points. Do you think that at some point we'll have wait, I said this. No, sorry, I said something. Here the axes of the certain row are not blocked. You just refresh the adjacent rows, and then you restart the counter for that certain row. So, yeah, do you think at some point we'll have too many refreshes? Sorry about it. Yes.
Do you know about the time complexity of that algorithm? Because I mean, if it's scalable and if it's easy to know which rows need to be refreshed when, then it's the ideal refresh phase mitigation technique, right? I think according to the papers was the best mitigation.
Okay, the complexity, I think it's like it doesn't count accurately the number of accesses. It's similar to a Bloom filter. It overestimates the number of accesses. It tries to keep track. It has a table, and whenever you access a row, you increment that counter, and if the certain address is not on that table, you go to a thing that I'm not remember the name, but it has like just access that were into the table, access to address that were not in the table, and you increment this counter every time. So yeah, maybe it's okay. This is a little bit hard because you don't know how the algorithm works. But yeah, the result of the paper is that this is a scalable solution. And one thing that I like about the paper is that it considered more than just performance hit. It also included area analysis and energy overhead. And as you can see, as you go to lower AC first values, graphene still works. Now the last paper, Aqua, written in 2022, and it also implements the Rise algorithm. But instead of refreshing the adjacent rows when you reach a certain threshold, the row address that was accessed too many times is moved to a specific area in DRAM, which is called row parenting area. Yeah, and do you think what do you think about this idea? I think that my main problems where the paper was it was related with maybe at some point there will be too much data movement, and maybe the size of the row parenting area will increase too much. What do you think? Yes.
Not special about this row parenting area.
It's just an area in DRAM. So you just move the rows to those addresses are addresses in DRAM, which are specifically and only used for to give rows that were accessed too many times.
And this is the like more spacing between the rows to.
No, it's just if you have imagine you have a basic first value of 1K and you access a row almost 1K, you'd move to this specific area in DRAM. So you can keep accessing the row because the new adjacent rows weren't affected by the previous accesses.
But what prevents row, I mean, if it's already there.
If it's already in the row parenting area, the paper implements an algorithm that moves to another row in the row parenting area. Yeah, I can read just the results of the paper. So the paper concluded that reserving 1% of the DRAM to work as the row parenting area was enough to mitigate RowHammer at 1K, and this only had a 2% performance overhead. So thank you for your time, and if you have any questions, I'll gladly respond.
Question. I'll make a couple of comments. It was a very good presentation. Thanks for being the first to present. I think it's very good that you covered a lot of related work also on the topic. And I like the nitty-gritty detail that you went into, and you found a bug in the paper, which is the column strike pattern. So that CO1 and CO0 should be CS1 and CS0 respectively. And hopefully that'll be fixed as soon as the archive revision. I don't want to say too much because we don't have a lot of time, but this was one of the papers. You got one thing wrong actually, which is the trespass versus this. These are both completely concurrent works. Actually,
Okay.
even though trespass was officially published in May 2020, this was published in June 2020.
I thought it was early because when I went to the references,
Yeah,
was there, so I assumed okay, trespass was really.
yeah, that's right. Yeah, they were completely concurrent works. But yeah, we put trespass a little early, but yeah, they were both motivated by this claim that
Because the paper also mentioned trespass proved that you were.
yeah, that's right. That we used it. So the final version was updated as things moved along. But these studies take a long time, so it was done concurrently. But yeah, you're right. It could be used that way. But these are works motivated because of those claims. As I mentioned last time when I talked about RowHammer, that RowHammer solved, and we looked at is that true in real DRAM chips as the trespass, and is that true at the device level, and that's this paper. So both of these papers actually pushed the industry to really solve the problem. And that's why also academia, as you mentioned, right, all these works that came after were motivated, oh, RowHammer is still a problem, let's solve it. Okay, I can go on, but you should probably transfer to the next presentation.
Thank you again.
Thanks. I don't know if people online can hear me, by the way. Speaking is far away.
Yes, we can. We can hear you.
Okay, good.
Maybe while transitioning to the other presentation, you can mention about the quizzes and the evaluation form. Is that okay, Onur?
Yeah, that's fine, but somebody probably should transition to the next presentation while you're talking.
Perfect.
No, that's not for you. I think you're done, don't worry. Mohammed will cover some logistics. Go ahead, Mohammed.
Should be on.
Yes, so I just sent an email over Moodle to all students and TAs about the evaluation form that we just released. So if you go to the Moodle page of the course, you will see 3 evaluation forms. One of them only for the mentors, so please don't fill it. I don't think you have permission to access it. The other is for the presenters only. So 2 students for today, they are going to fill it within 24 hours. And you will have some questions about your mentors and your experience within this course. The other evaluation form is for all students. So you have 24 hours to fill that. Please do so. It's on evaluating the 2 presenters for today. So you'll have very simple question to rate from 1 to 5 on how it went, whether well or not so good, and some comments on how to improve the presentation, what are the things that were not answered good, and so on. So feel free to answer anything within the feedback, but please submit it within 24 hours. And this is mandatory, so everyone has to fill it. For each presentation, for each student presentation, you have to fill that form. And another thing is the quiz. So after the 2 presentations, we will have the quiz, which is 3 multiple choice questions for each presentation. So we'll have in total 6 questions, and you also have 24 hours to submit your answer. As we promise, all the questions should be answered without reading the paper. So by just paying attention to the presentation, you should be able to answer those questions. I don't want to take more time, but if you have any question, feel free to ask us after the lecture. So Haosung or Ismail can introduce the student, and we can start with the second presentation.
Okay. Can you hear me?
Yeah.
Okay, cool. So yeah, hello everyone. Florian will go over this paper, MOESI-prime. Florian is a third-year bachelor student in computer science. He is interested in robotics, but also hardware design and algorithms. So yeah, Florian, please go ahead.
So, hello everybody, I'm Florian Portman, and I will be presenting MOESI-prime, preventing coherence-induced hammering in commodity workloads by lead author Kevin Laughlin. First, I'll briefly go over the executive summary. Now, for the motivation, still the same problem as the previous presentation, the decreasing activations needed to flip bits, and most likely future DRAM will have even lower RowHammer thresholds. This leads to the problem that the paper identified. During commodity benchmarks, Intel CC NUMA coherence protocols cause activation rates that surpass current RowHammer thresholds. Now, the goal paper is to identify the sources of this hammering and prevent or mitigate coherence-induced hammering. They present a new protocol, MOESI-prime. It's based on the MOESI protocol that already exists. And the key ideas are they add 2 new states and make some small changes to Intel's memory directory management policies. Finally, they basically prevent coherence-induced RowHammer without or with negligible effects on average performance, and they even improved DRAM power usage in some cases. Brief outline. First, I'll give you some background on the topic, then I'll explain the problem sources, then the solutions and the key ideas, the solutions, the evaluation of MOESI-prime of their presented method, and conclusion, and then the end, strength, weaknesses, and discussion. So first, a small background. This is a subarray of DRAM bank. See, the cells are aligned on a grid, and for this paper, for this topic, we will mainly focus on rows of such a DRAM bank. Meaning, when a row is repeatedly read or written to, or basically when a row is repeatedly activated, the neighboring rows can experience bit flips without being accessed themselves. This phenomenon is called RowHammer. And here you see a small program that simply moves a cache line, memory line into a register, then moves memory line Y into register, flushes both lines from the cache, then repeats this, and when this is repeated over and over, neighboring rows can experience bit flips. Now, this is malicious hammering or an example of malicious hammering, as such an access pattern has not yet been observed in commodity workloads or non-malicious codes. But for the paper today, the important difference is they observed dangerously high row activation rates in commodity benchmarks, meaning non-malicious codes. As you can see here, for example, on a producer-consumer benchmark, where a producer simply repeatedly writes two lines and the consumer repeatedly reads those 2 lines, they observe activation rates over 10 times as high as the current maximum activation count, which is the number of activations with a refresh window before any bit flips occur. And obviously, that's a problem. And so they went ahead and tested, find out what are the problem sources. And they identified 3 sources. First, downgrade writebacks. Secondly, memory directory writes. And lastly, speculative reads. I will briefly go over each problem source and give you some background and explain why they're a problem and what's the problem they cause. First, we'll talk about downgrade writebacks. Now, in MOESI-based protocols, the problem is that when a dirty line is shared, it must be written back first. And since Intel's cache coherency protocols are at least similar or based on or a variant of MOESI or use a variant of MOESI protocol, this is one of the problems. I will briefly showcase this with a writer-writer example, a writer-reader example, where we have C0 as a writer and C1 as a reader. And when C0 writes, the cache line becomes modified or goes into modified state. And more importantly, now C0 has a dirty copy of the line, while the shared memory copy is stale. Now, before C1 can read something important or something must first happen, that is the write back. Then, after write back, both can enter shared state, and now the shared memory copy will be up to date again. And this downgrade from modified to shared, and the write back that comes with it is the downgrade write back, which they identified as the first problem source. Now, the second problem source is memory directory writes. Again, a brief background on Intel CC NUMA system or architecture, how it works. And CC NUMA stands for cache coherent non-uniform memory access. Here you see two nodes, a local node and a remote node. I will shortly explain why we call them that. And they're connected by an interconnect, and each node has its own memory. Now, we call this node the local node because each node has a home agent. The home agent is responsible, or better yet, each address in memory is mapped to a home agent, and that home agent is responsible for the coherency of the address across the nodes. Now, we say in this case it's local node because we look from the perspective of this node and say this is the home agent. And the problem occurring now is the interconnect is less desirable than directly accessing local memory, or at least it might be a little bit slower, or we prefer to access local memory. And so when remote node requests a write or read from the local node, or the request arrives at the home agent, that request must be processed by the home agent. And if it does not know, maybe a remote node, a different third remote node might have this line dirty in its cache. So the local node must send a broadcast or a snoop on the interconnect to get the information about whether the different or what the current state of the line is. And then when it receives that information, it can return the request to the remote node. But this request, if for every request the local node has to snoop the entire network or the interconnect, that uses a lot of bandwidth of the interconnect. And so the solution used by Intel, for example, is a memory directory. Now, the memory directory is directly in the memory, and for each line, or next to each line, it encodes that line's remote state. And the memory directory encodes the following three remote states: A for snoop all, S for remote shared, and I for remote invalid. Now, I'll briefly go over all of them. Starting at the bottom, remote invalid means the line is not cached on any remote node, meaning it's safe to either return it's safe to not say that the local or the home agent does not have to snoop to all remote nodes because again, it's not cached anywhere. Then remote share means the line might be or is located or is available on a different node or on a remote node, but it's clean, meaning it's only shared, it hasn't been modified. And again, that means the home agent does not have to snoop because if it's clean, it's up to date with the memory, and so the home agent simply has to make sure that it's invalidated on the remote node, does not have to snoop the interconnect. And then the most important state, at least for the subsequent problems, is the snoop all state. It implies that it might be, not a guarantee, but it says that it might be that a remote node has a dirty copy of this the line, and so the snoop must be sent across the interconnect to determine whether that's the case, and if yes, then retrieve it. I will now showcase or explain what is the problem with the writer example. Again, we have a similar setup with a local node, a remote node, but this time we have a memory directory, and we track whether or not we do a memory directory write. And the initial state is the local and remote nodes both the line in cache is invalid, and therefore the memory directory is stated remote invalid. Now, when the remote node sends a write request, the local node knows that it must transition into snoop all state, as now the line will most likely or will be dirty in a remote node. So the local still invalid, remote is now modified, but the memory directory gets written to snoop all. Then when the local write happens, the local is modified, the remote is validated, and memory directory now remains in snoop all. This becomes a problem in the next step when we repeat this pattern of a remote write, local write, and remote write request arrives again. We notice that the snoop state is now stale, meaning that the home agent has no idea what the state is without looking it up. So it has to assume, or it has to conservatively write snoop all again to make sure that it is aware that a dirty copy exists somewhere else. And then that means memory is written again for the memory directory, and this is a redundant write as it was already in snoop all, but the home agent is not aware of that. And if we repeat this pattern over and over, this redundant write can hammer memory. And then on to the last problem, that is speculative reads. We add one more small thing to the structure shown before, that being the memory directory cache here. The rest of it is the same. The memory directory cache stores a subset of the lines that are in snoop all state of the memory directory, with the idea being that if a request arrives and the memory directory cache hits, because it stores lines in snoop all state, the snoop can be immediately sent without checking the memory directory. And if the memory directory cache misses, we still have to do first the LLC lookup. And if that fails, if the line is not cached here somewhere, we have to read memory. Now, Intel seems to use, it's not quite clear, the pattern suggests that Intel uses something along this. They start this LLC lookup and the memory read simultaneously to reduce latency, as otherwise they would have to wait for the local lookup and then if it fails, start the read. Now, this causes a problem. If the local lookup succeeds, this speculative read is unused. Again, same write-to-writer scenario, but this time we focus on the memory directory cache, not on the memory directory. we do the same step, we write, and now comes the problem. Intel CC/NUMA protocol deallocates the memory directory cache entry for a local write. Meaning, while there was an entry here stating that SNU call state, upon the local write, it's deallocated. Because, which generally will make sense, because when the local node is written, that would imply that the remote states are invalid. So when request arrives, it makes no sense that to send a broadcast to all other nodes as the current state of the line would be local, saved locally. But when we repeat this pattern now, remote write, we get a directory cache miss, which in turn starts the LLC lookup and the speculative read in parallel. But as we have just had a local write, this LLC lookup will succeed, and the speculative read will go unused. And these speculative reads, when repeating this pattern, can hammer memory again. Now, onto the solution presented in the paper. It's called MOESI-prime. It builds on top of the MOESI state that already, the current MOESI protocol that already exists. And importantly, it retains Intel's state-of-the-art memory directory design. Here is an overview of the 5 states of MOESI. We will mainly focus on these 2 states, as they are the most important for the problems, being modified and owned. Now, owned is similar to modified, but it allows multiple dirty copies to exist without writing back to cache first. When a remote node, for example, requests a read. But we will see this in more detail soon. Now, MOESI-prime adds 2 additional states to this protocol, being M-prime, which simply is the same as M basically, but it implies or it states that the memory directory state is A. And the same as O-prime, it's state O, but the memory directory state is A. And again, remember the 3 problem sources. We will go over how this solution solves each of them. First solution, or the first problem, was downgrade writebacks. Must write back 30 lines before sharing. The solution of the MOESI-prime is the addition of the O state to the MESI protocol. I will showcase this with a brief example. On the left, you see the MESI protocol and how it occurs these downgrade writebacks here from M to S. Now on the right, we look at MOESI. The initial state is the same, but when the remote read request arrives, the local node can transition into the owner, meaning it can directly share the dirty line without writing back to memory. And then on a local write, it's the same again. It transitions into the modified state, and the remote is invalidated again. But the essential part is the difference here. We had in MESI had a downgrade writeback from modified to shared, which required writeback, but in MOESI, there's no downgrade writeback. So conclusion is the addition of the O state eliminates downgrade writebacks. Now the second problem was memory directory writes. Again, the main problem, or summarized, is that the home agent is unaware of the state. If it knew that the state is, or if it knew it's in SNU all, it wouldn't have to write through these conservative writes. Hence, the addition of the M-prime and O-prime sets. Again, I will showcase this with 2 examples. First, again, writer-writer. As we've seen before, MOESI, it's the same as MESI. It's still write. The memory directory is written every time the remote write request arrives. And now for MOESI-prime, we say for initial state, we assume maybe a remote write has happened. And the important part is, upon a remote write, we know that the memory directory will be in A. And so instead of going to modify, we go to M prime. Same as because we had M prime before, we know it's in A, so we can transition to M prime in the local. We still know it's A. Same for the third write or the remote write again. We always know memory directory is in A as long as we're in M prime. And key difference, instead of going stale, it remains in A, or we can for sure say it's A. And for producer-consumer example, of remote producer, meaning remote writer, when it's basically the same, but one of the M states is switched with an O state, we can have the redundant memory write, memory directory write, and in MOESI, even though we added the O state, this still happens. So MOESI-prime, instead of M prime, it's now O prime, shared, and we know we're in Snoop ball state. And again, M prime, we know we're in Snoop ball. Therefore, we do not have to do this redundant memory write. Meaning, the addition of the M prime and O prime states prevent coherence-induced hammering directory writes. Lastly, we have the speculative reads, with the problem being that directory cache misses lead to unused speculative reads. Now, solution isn't to add a state, or it isn't M prime, O prime, or O, but instead they make a small, or at least a change to Intel's directory management policy. Now, this part is a little tricky because there isn't straight up information about what Intel currently does for the speculative reads, but a patent suggests, or a patent from Intel suggests that they deallocate, like I stated before. So instead of deallocating or not allocating a directory cache entry for local writes, as it probably wouldn't be needed, MOESI-prime retains or provisions an entry pointing to the local node, meaning if, for example, the remote write, the local write happens, we change this entry in the directory cache to point to the local node instead of the remote node, instead of deallocating it. And the consequence or the result is that the request for the contented lines almost always hit in the directory cache, and therefore there's less speculative reads that go unused, and those speculative reads no longer hammer memory. Now, I just wanted to briefly mention, the paper also contains a proof of correctness for their MOESI-prime protocol, which essentially uses the fact that it's based on MOESI to prove the correctness of the M prime and O prime state, and it proves the correctness of the directory cache modifications to ensure that the protocol still works as intended. Then we go on to the evaluation. The evaluation was done in the Gen 5 simulator, and MOESI-prime is compared to both MOESI and MESI protocols. Depicted here are the maximum activation rates for any refresh window within over the duration of an entire benchmark, meaning the highest activation rate in a refresh window over the duration of the entire benchmark. And as you can see, most important, or the key part, is the average. And compared to MESI, MOESI-prime reduces the maximum activation rates by over 70% for all configurations, meaning 2, 4, or 8 nodes. Additionally to the maximum activation rates, They also examined the speed up and power save of the RAM, and I only showed the results for 2 nodes here, but in the paper there's an entire table for all the benchmarks, which show for 2, 4, or 8 nodes the results. But overall, the averages are negligible differences, and power save is overall or average even a little bit better. Now, it's important to note that in some cases and in certain benchmarks, there was small performance loss, but again, it was compared to MOESI or MOESI, but it was negligible, so the result overall is quite good. The average is even slightly better. Now, onto the conclusions. They discovered a novel type of hammering called Coherence-Induced hammering, which, as opposed to other types of hammering, occurs in non-malicious code, which is a large difference, as it is a reliability threat, for example, servers. Instead of a security threat, there might be data corruption in regular workloads. And they presented MOESI-prime, their solution, that even prevents coherence-induced hammering. And the results are that it even sometimes improves or overall improves average DRAM power and has negligible effect on performance. Now, before I go to the last part, are there any questions right now? Okay, then maybe later then again. So first, I'd like to talk about the strengths. Like I said, it's a novel hammering, which they were the first to describe. They called it coherence-induced hammering. And again, it's also first hammering found in non-malicious code or occurring in non-malicious code. Their paper identifies the individual problem sources and tests the individual solutions, or tests the individual problem sources, identify them, and then based on individual problem sources, they propose a relatively simple solution based on existing protocols. They simulate their new protocol, and they evaluate it and compare the results with existing protocols, being MOESI and MOESI-prime, or I mean, there are more protocols, but they compare it to MOESI and MOESI-prime. They test multiple metrics like row activation rates, performance, and power draw, and they also include a small section on scalability, meaning the impact of the number of nodes on the performance. More nodes, does it not scale well for more nodes? And finally, like summary or the complete sentence would be: MOESI-prime prevents coherence-induced hammering without affecting performance. A small point for me that I noticed in the paper: their implementation and evaluation infrastructure, there's a link in the paper, and it's open source, can be found on GitHub. Then we move on to the weaknesses, which I had some difficulty finding, but I noticed a couple of small things. Firstly, in the benchmark results, there were some interesting or weird results. For example, the left, you see strong variability of the result between different nodes, and this for the speed up or for the execution time. On the right, you see I highlight or took some of the benchmarks. You see that MOESI-prime performs worse than MOESI, or sometimes even worse than MESI for some of these benchmarks. Now, they briefly mention this, but they don't really go into detail, and I'm not really sure because of this whether they investigated this more and determined it not to be a problem, or whether this is a possible area or possible point that needs to be tested further. Then, additionally, as a small weakness, there were 2 or 3 typos, 1 or 2 inclarities that are weird formulations, but overall, I think it's very clear and very understandable. And yeah, I guess we can move on to discussion now. And I'd like to ask if maybe you have an idea. Like I said, they go into it briefly, they mention some points, which I will mention shortly if if none of you has any, but what do you think? What are possible reasons for these increased activation rates for more nodes? In general, maybe to highlight real quick, you might notice in many cases, while for the other protocols the performance or the maximum activation rates decrease, for MOESI-prime it increases. Here or here, or even here, but here it increases for all of them. Again, same together with the other question. Any of you have an idea based on how MOESI-prime works, why that could be? Possible reasons? Okay, then I'll mention a couple. Now, again, like I said, they briefly mentioned possible reasons. First being increasingly strained scheduling. That is also the excuse or the reason they give for this variability. Meaning they say it's just that those benchmarks are very sensitive to scheduling, and therefore they experience this strong variability. But yeah, that's all they mention about it. Then, secondly, they talk about the protocols artificially reducing the directory cache size so that it's consistent over all the nodes. Now, I'm not entirely sure what they mean by that in the paper. Maybe some of you have an idea, because they don't really go into it, and I don't really see a concrete reason why they should reduce the directory cache size if more nodes are used. But that's what they mention. And then I guess most obvious or the clearest reason, if you have more nodes and the same directory cache size, the directory cache has to cover more memory in that sense. Meaning, for example, for 8 nodes, the directory cache has to cover 7 out of 8 nodes, or lines from 7 out of 8 nodes. And for 2 nodes, you only have 1 out of 2 nodes. So there's much more space in the directory cache. And in general, not concerning the weird data, what are possible reasons that, now not activation rates, but what are possible reasons that select workloads experience higher or decreased performance, meaning longer execution time than conventional protocols. Maybe as a reminder, MOESI-prime, for example, eliminates redundant directory writes. How could this impact the overall performance? Yes? No, not necessarily. I mean, they do less writes, right? They eliminate the redundant writes. But I mean, the idea is, for example, for this example, that a redundant write that would have occurred in the baseline protocols that is eliminated now might have either like activated a row that would be subsequently read and reduce the latency for that, or some other case where yeah, no, that's that case. It might have the redundant write that was eliminated might have actually activated it and brought it into row buffer, and then the subsequent read would have been a row buffer hit that would have reduced the latency for that subsequent read. And overall, if that occurs multiple times, that might increase decrease performance as these redundant writes. The read will be slower for MOESI-prime then. As another point, or maybe another idea, remember comment of the Intel's current solution deallocates upon local writes into the directory cache. So how could the provisioning or the retaining of the entry in the cache also decrease performance in the end? So there's more entries in the cache now, or more are kept in the cache. And that could lead to set conflicts and maybe even space, that there's not enough space in the cache for subsequent requests, and then certain entries are evicted, which then leads to unnecessary broadcasts, which takes more time and then decreases performance. And then I guess the last and simpler question I would ask you, maybe not even simply for the writer, but in general, the scenarios that I showed you of the remote producer and local consumer and local consumer and remote producer, also the writer, where do such sharing patterns occur? Or why is it that those are relevant for commodity workloads? Can you think of a program that you might have already written that uses a writer scenario, where two threads, for example, keep on accessing or writing the same data? Yeah.
I think any program that involves metrics, multiplications, for example, if you realize that you have multiple threads accessing the same entries to the matrix, or at least partially the same entries. Or for example, vector addition. If you divide a vector into segments.
I mean, exactly. So the entries have they cannot access the matrix at the same time, right? Or the same entries. And a general example would be block rotated data. Maybe the matrix or the submatrix is block rotated. Then when one node accesses it, it locks it and writes to the other node, and then they share these locks, ping pong them back and forth, write, and I mean, this is a common, or this could be something that occurs in regular code, which then causes this write-to-write scenario, which in turn would or could cause this hammering, like it's explained. Are there any questions now, maybe, or otherwise, okay? Yeah. So, do you have any remarks or any questions? Otherwise, thank you for listening.
Mentors are online.
Mentors are online, yeah.
Are they hearing us?
Can you hear us online?
Yes, yes, we can hear you.
Do you have any remarks, also?
We can hear you.
Maybe not exactly here.
Are there any remarks from the mentors or online?
Hello, hello.
Yes.
Yes, Hausung, they are asking if you have any feedback. We don't have question in YouTube.
Yeah, I don't have further comments.
Maybe I'll consider that. We're almost on time. That's good. So thanks for the presentation. I think this is a relatively tough topic, let's say.
I mean, it's relatively novel. I think
Yeah.
it's late or mid 2022.
Yeah, it's very new. So the first paper was from 2020. It was more of a characterization paper. It was more of a, let's say, attack paper. It's also not a full attack, right? Because they don't really develop a full attack that builds on it, but they show that the activation rates are much higher.
But I mean, there are attacks for coherence, or there are coherence-based attacks that, for example, use conflict-based.
That's right. Yeah.
That use set conflict. I mean, or at least to me, it seems like the key part here is that's not an attack, right?
Yeah. Yeah, typically don't have the activation rates are higher. So it's actually an interesting paper. Because this session was more of an attack and analysis of RowHammer session. And this sort of papers actually enable the industry to move forward. Really fix. You can see that some of the authors are from Microsoft.
Yeah.
Directly by just solving the problem. Microsoft, especially from the Azure perspective with their data centers. They were just looking at these attacks. Clearly. Any other comments? Because I don't want to take much more time. But since we discussed RowHammer quite a bit a couple of lectures ago, but now you've seen analysis. I'd like to mention one thing about the prior paper. So the prior paper, this sort of it takes a lot of time and rigor to do those studies. Like we were mentioning, why can't you find the labels, etc. But this sort of information doesn't exist. So you have to do a lot of reverse engineering, other analysis of data to decide what chip belongs to what generation. You cannot do this perfectly, unfortunately. Vendors are not very forthcoming sharing any kind of information. And here again, you can see that somewhat here also, right? This is a paper written by Microsoft and Michigan. They basically have hypotheses as to how potentially Intel's coherence protocol works, but they don't have exact information.
Yeah, mainly for the speculative part, it's mainly based on AMD. I think is really or more open about it, and they use something similar.
That's true.
But then again, the rest of the for example, the directory cache, I don't think AMD uses something directly comparable to that, and so it's unclear whether or not that is applicable the version that AMD uses. But I think, or at least it seems like because their results match or at least supported their hypothesis, it's likely that something at least similar to what they suspect.
Yeah, potentially that's true. But there are some cases, as you mentioned, that are not completely explained also. Maybe
Yeah,
because
or at least not.
they don't have enough information.
Yeah, probably.
Okay. There's nothing else. We're done for today then. Don't forget to fill out the forms and the quiz.